Alright, so let's proceed. Now we are given this beam and we are asked to calculate the support reactions at point A and point E, set up the shear force equation, draw the shear force diagram, set up the bending moment equation, and draw the bending moment diagram. These are just big English, just to make the whole something big. But it's simple. Now, to be able to determine these reactions at A and E, we need to set up what is called what? What's the first thing to do? Free body diagram. So apply the free body diagram, FBD. So we bring back the beam. At point A, which support is this? And for the regular support, how many reactions do we have? Just one reaction. So we have here perpendicular to the surface, at 90 degrees. So it's still going to be vertical there. So we call this RAY. At B, we have a 5 kilonewtons force. Yes.
This free body diagram,
Reason?
does it have any mark?
Yes, it has. Yes, free body diagram has about 1 mark. A whole 1 mark. Okay, this is B. Now, between C and D, we have what? A UDL. To convert a UDL to point, what do you do? By the length covered, right? The length is what?
4.
So 4 times 5 gives us what? 20 kilonewtons. That becomes the point load. Where do we now place this point load? And the middle of 4 is what? 2, which is simply what? 4 divided by 2, right? So we simply have this point load here at the middle of the length covered. And 4 times 5 gives us 20. So the point load for the UDL is 20 kilonewtons. From C to the point load is simply 2 meters. From the point load to point D is also 2 meters. Finally, at point E, we have how many reactions there? 2 reactions, because what we have here is simply what? A pin support, right? And for a pin, we have 2 reactions, one vertical reaction and the other horizontal reaction. So this becomes REY and this is REX. So please take note. The reaction, especially the horizontal reaction, always points into the surface where it is acting. So notice that if we want at point A, I usually want to put it here, pointing into the surface. Same thing happens here at point D, it must also point into the surface. So this becomes the free body diagram of the whole system. So put in your distances. Here is 2 meters, here is also 2 meters, and finally we have it in 4 meters. This becomes your free body diagram. A whole 1 mark. 1 mark. After this time, what's the next thing to do? Employ what? Your equilibrium equation, right?
Yes, sir.
Beautiful. We have that summation of force in the horizontal axis is equal to what? That's the first equilibrium equation. Summation f of x equals 0. How many forces are pointed to the x-axis there? 1, which is what?
REX.
So this simply implies that REX is equal to what?
0.
Because only RES point to the x direction, so RES becomes 0. The second equilibrium law, summation of force in the vertical axis, summation f of y, is equal to 0. We consider vertically upward forces as what? Downward force as what?
Negative.
Okay, so let's start. At point A, we have what? RAY, right? So the value becomes what? RAY is positive because it's what? Pointing upwards. At point B, we have the 5 kilonewtons force acting downwards. What becomes that value? Minus 5. Next, we have what? If 20 kilonewtons force acting downwards, it becomes what? Minus 20. Finally, at point E, we have REY pointing upwards. That's simply what? Plus RE. And the whole of this is what? 0. So simply, RAY minus 5 minus 20 is what?
Minus 25.
Minus 25 plus REY equals 0. So let's simply send minus 25 over to this side of the equation. And if we do that, we simply have RAY plus REY to now be equal to what? 25. So call this equation 1. So take note, negative sign crosses an equal to sign becomes what? Positive. You have that equation. So equation 1 happens to be what? A single equation having how many unknowns? So which means what else do we do now? Take moment. And which place is best to take moment on this day? About point E. About point E. Take moment about the point where we have what? Numerous of forces. Okay, so E is better for us to take moment. Taking moment at point E. Okay, and we know that summation of moments at point E from every wrong law is equal to what? 0. So let's consider clockwise to be positive, anti-clockwise going to be negative.
Excuse me, sir.
Yes.
Why are we taking moment at point E instead of point A?
You can see take moment at point A, you have the same answer. Take moment at any point, you have the same answer. Now, the reason why I always lay emphasis on taking moment at point E is when you encounter forces like three-dimensional force moment and maybe in thrust analysis. I always say take moment about the point where you have what? Numerous of forces. If you have that idea from the beginning, it helps you. That's why I always emphasize, but it doesn't still matter. If you take moment at point A, you still have the same answer. I think I've done that in class before. You can even not go through this equilibrium law. Just take only moments. Moment at point A, you have RAY. Take moment at point E, you have RAY. Have the same answer without even going through this equilibrium law. I've done it in class before. Alright, so let's take a look at point E now. We said let clockwise be positive and anti-clockwise negative. Let's start with this force, 20 kilonewtons this force. This force is pointing downwards, which means the line of action is downwards, and therefore the moment of this force will turn about in this direction. Is that also? Is it positive or negative? Negative, so it's anti-clockwise. And what is the distance it takes this force to get to point E? 6. 2 plus 4. So you simply have minus 20 times 6. Same thing here, you have a 5 kilonewton force acting downward, which means this force will turn about in this direction. Negative or positive?
Negative.
Total distance it takes to get there is what?
8.
Are you sure?
6.
No, 10.
10.
So you simply have minus 5 times 10. And finally, this force is pointing upwards, RAY, which means it will turn about in this direction to take moment at point E. Positive or negative?
Positive.
Total distance is what?
12.
So you simply have plus REY times. The whole of this 0. Sorry, REY. The whole of this is equal to 0. So from here, minus 20 times 6. Minus 120. Minus 120. Minus 5 times 10 is minus 50. And plus 12 RAY, and this is equal to 0. Minus 120 minus 50 minus 170 plus 12 RAY equals 0. So simply send what? Minus 170 over to this side of the equation. Negative sign, constant sign, equal to sign becomes what? Positive. So you simply have 12 RAY will now be equal to 170. So to make RAY subject, divide both sides by 12, which means RAY is actually 170 all over 12. Please give me the value for that.
14.17.
14.17 kilonewtons. So that becomes the actual at point A. If you know RAY, what do you now do?
Equation.
Into where? Equation 1. Okay, so that means from 1, we have RAY, which is now known as 14.17. So we have 14.17 plus RAY, and that's simply equal to 25. Okay. So of course, you make RAY subject simply by sending 14.17 over to the second equation. Okay. So we simply have RAY is 25 minus 14.17. This implies that RAY is what?
10.83.
83 kilonewtons. So this gives you the reaction at that point. So that's the first question. Support reactions at A and B found. And I said, after obtaining this, because we have a UDL on the beam, you now put in this value of the reactions back to the what? Original beam. not the free body diagram. Please take note. You put in the values of the reaction into the original beam and not the free body diagram because of this UDL. So if we do that now, we have bring back the beam. We know support at point A. Okay, RAY. The value gave us 14.17 kilonewtons. And point B, we have a downward force there, 5 kilonewtons. Between C and D is a UDL. So put back the UDL, very, very necessary. Then we'll have REY at point E. REY give us 10.83 kilonewtons. So distance apart 4 meters, 4 meters, 2 meters, 2 meters, right? Yes. And the value of the UDL will remain 5 kilonewtons per liter. So you put it back into the original. Now we can start the shear force analysis. The second question says set up the shear force equation. So let's do this now and see. I said shear force simply means what? The stepwise summation, right? Of the entire force acting on the beam from beginning of the beam to where? To the end. We consider upward force as what? And downward force as what? Beautiful. So let's do that together now and see. Shear force is point A, this is point B, this is C, D, and E. Shear force at A is simply what? 14.17 kilonewtons. So the force that exists at point A is the shear force at A. And that force is upward, so which means that force is positive. It means shear force at A is simply 14.17 kilonewtons. And I said this force moves from point A down to what? Point B, right? So we simply have shear force what? B prime. Which means initially this shear force moves down to point B, it still remains what? The same value, and that value remains what? 14.17 kilonewton. But on getting to point B, this force now realizes that I have what? A downward force at where? Point B. The value of that downward force is what? 5 kilonewtons. So if it is downward, it means it's going to have a value negative. So we simply have the shear force B prime prime, which means finally at point B, this force 14.17 kilonewtons now encounters a downward force of what? 5, which is simply minus 5. What is now the value? 9.17 kilonewtons. So this becomes the shear force at point B. Now this same shear force moves from point B down to point C. Now please take note, do I have the force at point C? No. There is no force at point C. Since there is no force, then I will simply say shear force at point C. Had it been there was a force, I would have said C prime. Just like I did at B prime, because there was a force at point B. But since there is no force at C, I will simply say shear force was C. It is this same force that moves from point B down to what? Point C. We simply call that 9.17 kilonewtons. This is clear, right? But along moving from point C down to point D, it now encounters what? A UDL. Is that not so? And I said because of this UDL, we're going to do what? Take a section. So you consider a section XX at a distance of what? X from A. So distance from point A to the point of section is simply what? X meters. So if that's the case, what now is the length of the UDL about the point of section? That's simply from point. Beautiful. From point C to the point of section. It's not okay. See the same thing. You see the same thing. It's not calculated, but you see the same thing. You see the same thing. That's how you get the distance. So I said that if we take a section along the UDL, because we have a UDL, it's a different kind of loading. It's not the normal loading though. It's a different kind of, so we need to find what is the length of the UDL. Because of this UDL, we have to form what is called a UDL equation. I mean the shear force equation. That's what this thing is saying here. Set up the shear force equation. Because we have a different kind of loading on the system or on the beam, we have to form an equation. To form this equation, due to this UDL, we can simply take a section along what the UDL, which is along CD. So you consider a section XX at a distance of X from A. So always that distance from point A to the point of section remains what? X. Okay, so if that's the distance now, what is now the distance of this what? UDL from point C to the point of section? simply take away every other distance is what? Behind. To get that distance, since I'm at point C, I don't need distance from point B to C, I don't need distance from point A down to C. So this distance behind, take them off from what? X. That gives you the distance from point C to the point of section. And how many distance do we have behind?
4.
2 plus 2, which is 4 meters. So which means the length of the UDL from point C to the point of section becomes what? X minus 4. X minus 4. Simply take away this distance you don't need from X. That gives you the length of the UDL. Not forgetting, this shaft becomes shear force along where CD. So it becomes shear force along CD. Shear force CD. And don't also forget, it was this force, 9.17 kilonewtons, that moved from C to D, now encountered this UDL. So you break down the force, 9.17 kilonewtons. Now, does UDL have a downward force or an upward force? So which means the value is going to be what? Negative. So you simply have negative. So now you know that the length of this UDL, by virtue of this section, the length of the UDL is x minus 4. What is now, to convert this UDL now to point two, what is it going to be? 5 times x minus 4. Remember, to convert the UDL to point two, simply what? Multiply the UDL by what? The load, distance covered. Now, if the distance is x minus 4, it means the point load becomes what? 5 times x minus 4. So you simply have here times 5 into x minus 4. This becomes the shear force. Now, this is the shear force equation they're asking this about. Set up the shear force equation. That is this. Okay, but the aim, of course, is to obtain what? Shear force at point D. We've obtained shear force at C. Next is to find what? Shear force at D. Is that also? Now, at D, what is now the value of x? Simply what? 8. As dx extends from point A down to point D, that means it becomes total length from point A to D, which is 2 plus 2, 4, plus 4, 8. Is that clear? Okay, so at dx equals 8. So this simply implies now that shear force at point D is now equal to 9.17 minus 5 into, in place of x, you simply put 8 minus 4. And this is now equal to 9.17 minus 5 into 8 minus 4 is 4. We simply have 9.17 minus 5 times 4 gives us 20. So this means shear force at D is equal to what? Minus 12.10. Point what? 83 kilonewtons. So this same force moves from point D down to where? Point E. But because I have the force at point E, what will I call this now? I will call that shear force what? E prime, which is initially at point E. So this same force moves, therefore shear force E prime initially at point E, this same force moves and we have minus 10.83 kilonewtons. But on getting to point E, it now realizes that look, I have an upward force there at that point. Is that also? And that force is going to be what? Positive. So I'll simply now say finally at point E, which is shear force E prime prime, is simply like equal to what? Minus 10.83 plus 10.83. And the value is simply what? At the end of every shear force analysis, you must obtain what?
0 as the answer.
Is it not sweet?
It's sweet,
But very sweet. So they say set up the shear force equation. This is the shear force equation. After the shear force analysis, they say draw the shear force. We'll do all that later. Let's get to the bending moment. I like to draw my diagrams in one. So let's get to the bending moment. Bending moment analysis. Okay? From equilibrium law, the moment of every force from the beginning of the beam is what? 0. So moment at point A automatically becomes 0. There is no bending there. Moment at A equals 0. Okay? So we now move to where? Point B. The moment of force about every point is also what? from equilibrium law, moment of any force about any point is simply what? 0. This force, 5 kilonewtons, does not have any distance about point B. The force is already at point B. So which means I can't take moment of this force about point B. The moment of this force about this point becomes 0. But I have a force here behind 14.17, which has a distance to the point B. So which means this force can take moment about this point. Is that also? And I said, when taking moment, consider upward force to have what? Positive moment. So which means moment at point B is simply what? 14.17 times distance it takes to get to that point is 2. What's the value?
28.34.
28.34 kilonewtons meter. That becomes the moment at point B. Okay. Now let's fall back here now. Okay, moment at point C, right? Yes. Moment at C. So we consider moment at point C. So since we are at point C, we have to take the moment of the two forces behind down to where? Point C. So the moment of this force, 14.17 to point C, means this force times total distance it takes this force to get to point C. And then moment of this 5 kilonewtons force times distance it takes to get to that point as well. But this force is acting downward, don't forget it. Downward force must always have what? Negative moment. So the moment at point C simply becomes 14.17 times 4 minus 5 times what? 2. So this is now equal to 14.17 times 4.
56.68.
What?
56.68.
68 minus 10, which is actually what? 46.68 kilonewtons meter. Now, moving along CD, we found out that there's a UDL, right? Okay, we've already explained this. And we'll take a section. Because of this UDL, we'll consider a section XS at a distance x from point A along the point of section, which is this. And we've established that the length of this UDL about the point of section is simply x minus 4. Is that also? Now, we want to take moment about the point of section. Please take note. Remember that when we were at point B, we took moment of this force to point B. When we got to point C, we took moment of this same force and this force to point C, right? So that means at the point of section, we also have to take moment of all the forces behind down to the point of section. So if from point A to the point of section is x meters, what is that the moment of this force about the point of section? Beautiful. Now, from point B, which means we also need to find distance from point B to the point of section. Because from point A to section is x, what is that distance from point B to the point of section? X minus 2. Simply take away this distance you don't need from behind. So that means that from this point to the point of section simply gives you x minus 2. And therefore the moment of this force becomes what? 5 times x minus 2. Force times distance, and distance is x minus 2 because 5 times x minus 2. Okay, now let's do that and see. So the first force, moment along CD, consider section SS at x from A along CD. So moment along CD is now equal to the first force 14.17 times x minus, because it's a downward force, 5 into x minus 2. Okay, now let's fall back to this UDL. Moment is force times distance. So first of all, we need to find the force of the UDL. The force of the UDL becomes what?
The force of the UDL becomes 5 times x.
Okay, so you have, remember it's negative because it's pointing downward, minus 5 times x minus 4. But this is not a moment, right? This is a force. So where do you now, what is now the moment?
X minus 4.
Beautiful. Let me explain now. This is the UDL. This is the point of section XX. This is point C. And distance from point C to the point of section was established to be x minus 4. So to convert this UDL to point B, what do? Multiply this by what? X minus 4, right? Then after converting, where do you place this point load now? Middle. So this is somewhere around here. 5 times x minus 4. This is the point load. That means from C to the point load is what? X minus 4 all over 2. Is that also? And from here to this point is also what? X minus 4 all over 2. The moment of this force about the point of section becomes what? This force time total distance it takes for to get to the point of section. And what's the distance?
X minus 4.
That means this becomes 5 into x minus 4 times x minus 4 all over 2. So, moment along CD. Okay, so at D, x is equal to 8. Okay, so moment at point D is now equal to, this becomes 14.17 into 8 minus 5 into 8 minus 2 minus 5 into 8 minus 4 into 8 minus 4 all over 2. And this is equal to, please, 14.17 by 8. 413. Okay, 113.36 minus, this is 5 into 8 minus 2 is 4, 6 minus 5 into 8 minus 4 is 4 into 4 again all over 2. Okay, so moment at D is now equal to 113.36, right? Which right?
Yeah.
Okay, yeah. Now minus 5 times 6 is 30.
Yes.
Minus 30 minus it should be 80.
70.
Is it 70?
Yes.
Are you sure? It's 80.
You cannot make
This is 20.
80.
Yeah, 80.
What divided by
Yes,
80?
it's about 80.
This is
Yeah,
20. Are you sure?
Yes.
5 times 4 is 20. Divided by 2 is 10. Times 4 is 40.
It's 40. Divided by 2 is 40.
80 over 2 is 40.
Okay, so give me the moment at point D. 1.336. 113.36. 43.36 kilonewtons meter. So that's the moment at point D. And the final moment is at point E. Now I said that since you enter the terrain of the UDL, you continue what? Taking section till the end of the beam. For bending moment, as you can see, it only applies for what? Bending moment analysis. You continue taking section to the end of the beam. So you consider a section, again, section XX at X from A, always is from A. Now it's going to be along the last portion, which is what? DE. Along DE. So let's see do that now. Now we're simply saying that we're simply taking the section here, XX, and distance from point A to this point of section still remains X meters. So of course, the distance of this man doesn't change. It's still X minus 2 to the point of section now. Distance of this load simply will take away distance behind. So it all remains normal, X minus 2. What is now the length of the UDL about the point of section? This is your problem. Light. Right? Okay, now what's the length of the UDL first?
X minus 8. So it's X minus 8.
8 or 6.
X minus 8.
Let's
So it's X minus 8.
No?
Because it's X minus 8.
X minus 8?
Yes, because when
Yes, correct. Yes, it's correct. X minus 8, yes, correct. It's correct. Yes, X minus 8. Yes, X minus 8. But how do you get X minus 8? Let me show you 2 ways to get this. 2 ways. 2 ways. Naturally, the length of this UDL is what?
12.
No, UDL. 4 meters, right? What's the length of the entire beam? 12, right? 12. What can I remove from 12 to get the length of this UDL? 12 minus 8. Remember I said I'm taking a section along DE, which means eventually I will say when x finally get to point E, at E x becomes equal to something, right? At E, what is the value of x? 12, right? So in place of this 12, simply call it x. It becomes what? X minus what? 8. That's the first shortcut. Second shortcut, I want just this. So which means I don't need this 2 plus 2. I don't also need this. I only need from C to D. That's the length of the UDL. 2 plus 2 is what? 4 plus this 4 is what? Simply remove that 8 from x. It gives you x minus 8. That's the length of the UDL. Is it clear? Yes. Okay, so that gives you the length of the UDL. But it doesn't end here. Now let's take moment about DE now. This one becomes moment along DE. The moment of this force, 14.17 kN, about the point of section is what? Times x. So you see how 14.17 times x, okay? Minus 5 into minus 2, right? Beautiful. Now we want to take the moment of this UDL. Yeah? Any errors? S minus 2 is correct now. It's correct. Now we want to take the moment of this UDL about point E. First of all, we need to convert the UDL to what? Point load, right? Convert it to load first. To convert to what do you do?
5 minus x minus 8.
Okay, so remember, minus 5 times x minus 8. So this is what a point load, but not a moment. Don't forget, not a moment. So if the length, now this length is not about the section. This length is the UDL length from C to what? Point D, due to the section. The length is given as x minus 8, right? So if I convert this, it becomes x minus 8, that's the point load. So it means that I place it at the middle, right? Which is simply 8 on x minus 8 over 2 times x minus 8 over 2. But this is between C and D, not the point of section. So if I want to take moment about the point of section, from D to the point of section, which is somewhere around here. Okay, now let's say because the whole aim is to take moment at point E, right? That's the whole aim, to get moment at point E. So which means distance it takes to get to point E from here, this is point E now, is simply going to be what? 4 meters, right? That's from D to point E. So what is that the moment of this force about point E? It becomes 5 into x minus 8, right? Times total distance it takes this force to get to point E, which is simply what? X minus 8 over 2 plus 4. Because the aim is to eventually take moment at point E. If I've converted this force to a point load, it will act at the middle. Middle of length is x minus 8 over 2. X, but this is between C and where? D. I want to take moment at point E. So total distance it takes this force to get to point E is simply what? X minus 8 over 2 plus E, which is plus 4. Now total distance it takes this force to get to point E becomes x minus 8 all over 2 plus 4. And if you do this, you don't obtain 0. Change my name from the head. I permit you to. Now let's try it and see. So at E, what becomes x? 12. Total length of the game. I think I'll wipe all this now. So moment at E is now equal to, we have 14.17 into x, x is 12, minus 5 into x here is 12, becomes 12 minus 2, minus 5 into 12 minus 8 into 12 minus 8 all over 2 plus 4. You have to manage this. So this is now equal to 14.17 times 12. 170.04 minus 5 into 12 minus 2 is 10, minus 5 into 12 minus 4 here is 8, into
4.
sorry 4. Okay, into 4. 4 plus, okay, no, 4 over 2 plus 4. Okay, so this 12 minus 8 is 4 all over 2 plus 4. So this is equal to 170.04 minus 5 by 10 is what? 50. Minus 40 into this is what? 20 into this is 2 plus 4. My brother, at this point, this is 170.04, right? You can simply call this 170. You don't need to put it 04. Keep it as 170. Okay. There's no need to put the 04. This is now 170. Okay. Minus 50 minus 2 plus 4 here is 6. 6 times 20 is 120. Do this and give me the answer.
0.
There's no two ways about life. It's either you're going to heaven or you're going to hell. You can't go to the two, it's not possible. At the end of every bending moment analysis, you must obtain 0 as the answer. There's no two ways about it. That is it. You can see how sweet it is. Is it not sweet?
It's not so.
Yes.
Can you do me a favor?
Please, what's the favor?
Can you explain from NT to AD?
From MD?
Yes, sir.
Okay, this side?
Yes, sir.
Okay, no problem, I will. Now, I said that immediately you enter the terrain of the UDL, you must continuously what? Take section T where? The end of the beam. Okay, now we are done with the first section. We not comment about point A. So simply what? Because of this UDL, take another section XX. From point A to the point of section still remains what? X meters. If that's the case, then the distance of this load about the point of section is still the same thing, doesn't change. Simply remove these two behind. This is my point B from X. It becomes X minus 2. But now I need to find the length of the UDL itself. I need to find the length of the UDL CD. So normally I know that CD, the length of the UDL is simply what? 4 normally. And eventually I know I'll get to point A. And for that reason, if here is 2 and here is 2, here is 4, 2 plus 2 plus 4 simply gives me what? 8, right? So to get the length of UDL, simply will take away that 8 from what? Because I only need from C to D. That's my second shortcut. I only need from C to D. So cover this point together. The only point I'm seeing now is what? 2, 2, and 4, which I don't need. I don't need 2 plus 2, 4 plus 4, 8. So simply take away that 8 from it. It becomes X minus 8. That becomes the length of the UDL. Now, after obtaining the length of the UDL, you find the length of every other load on this beam about the point of section. You now take moment. First is moment of this force, 14.17 about the point of section. Distance from point A to the point of section is what? X meters. Therefore, moment of this force becomes 14.17 times what? X. What to have here? 14.17 times X. Okay, next is what? A 5 kilonewtons force acting downwards. Distance it takes this force to get to the point of section is X minus 2. So the moment of that force becomes 5 times X minus 2. Now, we have the UDL. The UDL now has a length of X minus 8. Now, to convert this, first of all, UDL to point load, you have to find the what? Load first of the UDL. You have to simply what? Multiply the load intensity by what? Length covered. Simply 5 times X minus 8. That gives me 5 times X minus 8. That becomes the point load of the UDL. And let's say, place this point load there at the middle of the length. The middle of X minus 8 becomes what? X minus 8 all over 2. X minus 8 all over 2. This becomes the middle of the UDL. But the intention is to take moment at point E. So from point D, I will take point at point E, which means I still have 4 meters to get to what? Point E. Is that not so? Therefore, the moment of this force about point E becomes what? This force 5 into X minus 8 times total distance it takes this force to get to point E, which is simply what? X minus 8 over 2 plus this distance 4 meters, which is from here to this point. Okay, 4 meters. So that means the moment of that UDL becomes 5 into X minus 8 into X minus 8 over 2 plus 4. Now this becomes my moment. Eventually I will get to point E. So at E, X becomes total length from point A down to point E, which is simply what? 12 meters. So anywhere you see X, simply put the value as 12. You have 14.17 times 12 in place of X minus 5 into X here is 12 becomes 12 minus 2 minus 5 into X minus 8 becomes 12 minus 8 into X minus 8 becomes 12 minus 8 over 2 plus 4. And if you do the whole of that, 14.17 times 12 is, he got 170.04. So I said, of course, in an exam condition, don't, in fact, go with what? Accurate value. Just come out, remove that 0 point something. You have to be wise, you have to be smart. Because if you don't remove it here, we'll have 0.04. Is that also? Even if it's still 0, but don't just be smart along the line, remove the 0.4. It doesn't mean anything. You have 170. And if you evaluate the whole of this, you still have minus 50 minus 20 is 170. 170 minus 170 gives you 0. That becomes the bending moment analysis. So the remaining thing now is to what? Draw the diagrams. Is that also? That's the only thing left. And my hands are tight. I will need somewhere to plot this diagram. So you have shear force at A, 14.17, B prime 14.17. I will also need the moment equations too. So you just, yes, I will clean this side. This side looks easier to be compromise it. So all you need to do for me now is please keep shear force A for me. I think I will need shear force B prime and 2. Everything we are dealing with is what? The very last value, that's prime for the shear force, the very last value. Shear force B prime, if there is C prime times and E prime, I think there's E prime and here. So that's the only thing we are doing, and shear force A, shear force C. So you keep shear force A for me, shear force B prime, and shear force C, 9.27. So by right, these diagrams you're supposed to use graphs to plot it, but they usually allow free hands. Since you're still going to do more circle with graph, so they usually allow free hands. This reaction gave us this point A. We have 5 kilonewtons here. This point B, which is C and B. Not forget to put back your UDL, and then we have point E here. This reaction is what? 14.17, right?
Yes.
And here is simply what? 10.83. So to draw the diagram, all you need to do is simply trace out all these points. Trace out point A, trace out point B, trace out point C. So this is just like your graph, B has scale, and then point A. So we'll start with the shear force diagram. So look at the shear force values. Give me the highest from the lowest. Is the highest, right? Okay, so we have, let's keep it here, 14.17 kilonewtons. Yes, go on. 9.17. Followed by 9.17. 9.17. Okay, go on. Okay, 0 mark. So this is the origin, 0. Minus 10.83. So this is the 0 mark. That's the origin of the graph. Everything above the graph, the origin is positive, while every value below the origin is negative. So that's why I have a minus 10.83. So trace out all these points, just like you have on the graph sheet. Trace out all these points. Trace out all these points. Shear force at A is what? 14.17. This is line A. This is 14.17. So you simply asterisk where they meet. Shear force at B, that B prime, which is 9.17. This is line B. This is 9.17. This is where they meet. You asterisk. Shear force at C, also 9.17. This is line C. This is 9.17. You asterisk where they meet. Shear force at D. This is line D. This is minus 10.83. This is where they meet. You asterisk. And finally, E is 0, right? Yes. This is line E. 0. Now, I said the shear force diagram for a point load is simply what? A straight line connecting the points. So at point A, we have a 14.17 kilonewtons load is a point to going upward. So from the origin, you connect the straight line towards point A. This force moves from point A down to point B. Now encounter a downward force. So you come down to connect to these points. This same force moves from point B down to where? Point C. Now, between point C and point D, there is what? A UDL. The shear force diagram for UDL is what? A slant line. So you simply use a slant line to connect what? These 2 points. So you connect with a slant line down to point D. This same force moves from point B down to point E and then finally encounter an upward force and took it to 0. So you have that. This becomes the shear force diagram. So you can simply shape. That's the shear force diagram. Then bending moment diagram. Give me the bending moment values from the highest to the lowest. 46.68. Go on. 43.36, yes. 28.34. Any other value? 0. Is there a negative value? No. So they are all positive. So this is the origin. Okay. So trace out all these points. Trace out all these points to the end. Trace out all these points to the end. Trace out all these points to the end. Shear force at A is what? Sorry, bending moment at A is 0, right? This is line A. This is 0. So we are steady. Bending moment at B is what? This is line B. This is 28 points. So this one you meet, you are steady. Moment at C, 46.6. This is line C. This is 46. You have this is the maximum bending moment. See that I was telling you now? This is the value of the bending moment that has the highest value is the maximum bending moment. And it occurs where shear force changes sign from positive to negative. And you can see it. So it occurs directly at point C. That's the value of the highest bending moment. So if you have 2 UDL, it means the point where this bending moment is highest. Look at the point on the beam, where the shear force changes sign from positive to negative. That particular sign becomes the shear force equation that we're going to present to them. Is that okay? Okay, give me moment at D. 43 points. This is line D. This is 43 points. This is where they meet. And of course, moment at E is 0. So you simply have it. And I said the moment diagram for a point load is what? A slant line. No, a point load. We'll have a point load from point A down to point B. There's a point load. So this is slant line. Join them together. The same thing from B, also a point load down to point C. So a slant line. But between C and D, we have what? A UDL. So that for the moment diagram for a UDL is what? A curve. So you simply have this curve. So you see that this bending moment took place between where C and D. Is that clear? Okay. Then from D, of course, that is the point to that, so down to point E. So slant line connect to point D. This becomes the bending moment there. You can see how beautiful this diagram is. Wow. Bending moment diagram, and this is the shear force diagram. You want to find point of contraflexure? Now, there is no point of contraflexure here. The point of contraflexure is that point where bending moment changes sign from positive to negative. Does it change sign here? So it means POC is 0. Meanwhile, the point of maximum bending moment is the point where what? Shear force changes sign from positive to where? Negative. And it occurs between these 2 points. From point C to point B, this is where it changes from positive to negative. So that means point of maximum shear force, point of maximum bending moment is here in this equation. So look for the equation that belongs to CD. Shear force equation at CD equals to 0. Find the value of X. That point gives you the point of maximum. Let's do that. And there are 2 ways of doing that. I've shown that before in this class. There are 2 ways. The first way is the normal way I'm going to show you. Then the second way is for the Lights. Those are ready to that point. I'm going to show you the 2 ways now. I will show you the 2 ways. Okay, this is the equation there. At the point of maximum bending moment, the shear force equation is equal to what? 0. At bending moment max, shear force equation that's at CD is equal to 0 because bending moment occurs where shear force changes sign from positive to negative, which is at C and D. So the shear force equation at this point becomes 0. So it means the whole of this equation becomes 9.17 minus 5 into x minus 4 is now equal to what? 0. Simply, let's send minus 5 into this over here. We simply have 9.17 equals the whole of this goes there. Negative sign constant and equal sign becomes positive. So I simply have 5 into x minus 4. And I said to make this easier for you, don't go ahead to expand these brackets. That would be like a waste of effort. To make it easier, simply divide it by what? 5. So 5 cancels 5. 9.17 divided by 5 gives you what? So simply choose 1.8 equals to x minus, of course, you have 5 cancels 5, so left with x minus 4. Therefore, x is actually 7 minus 4 over here. X becomes 4 plus 1.8, which means the point of maximum bending moment exists at here 5.8 meters, approximately 6. Approximately 6. And let's check. Let's check now. This is 2 meters, right? This is also 2 meters. And this is where bending moment changes from positive to negative, so we are around there. So if here is 2 plus 2 is what? 4. They are telling you from this point to this point is what? 1.8. And if you check the distance, this is 2 plus 2, 4. So you can actually say this is either 6 or 5.8. Is that also? Because this could be even the middle. And this place is 4. Remember, this place is 4 meters. And if you divide it, it becomes what? 2. So 1.8 can also be approximated as what? 2. That's the point where bending moment is maximum. That's